Good evening to the Vice Principal, Student Life, Professor Themba Musee. Our speaker this evening, Professor Ndeke Musee, members of the UP Executive, Deans and Deputy Deans, Professor Michael Daramola, the head of the Department of Chemical Engineering, and our other heads of departments, our academic professional staff and colleagues, family of Professor Musee, ladies and gentlemen. It is indeed wonderful to have so many of you attending today's inaugural address. Welcome to this inaugural lecture to be presented by Professor Ndeke Musee. The title of his inaugural lecture is Anthropogenic Activities, Implications to Aquatic Ecosystems and Integrated Response. We are indeed privileged to have our Vice Principal, Student Life, Professor Musee, to officiate at this inaugural lecture. Please join me now to welcome Professor Musee to formally open this event and introduce the speaker for the evening.
Thank you very much, Professor Yelov, our acting dean. And good evening, ladies and gentlemen. On behalf of the Senate of the University of Pretoria, I would like to use this opportunity to welcome one and all present here, this evening. And I'm sure you will be able to enjoy with us the lecture from Professor Musee. And I would like to welcome a special word of welcome to him, Professor Ndeke Musee, and of course, members of his family and friends, head of the department, as the dean has said, Professor Michael Daramola, and colleagues, as well as the executive present here, the acting dean himself, Professor Yelov, and deputy deans, Professors Johan Joubert and Professor Walter van der Merwe, as well as members of senior management and our students. Ladies and gentlemen, when I was preparing for this event, I read Professor Musee's CV and abstract. The first thing that struck me is that he was born on the 1st of December. And apart from this being an auspicious occasion on account of his inaugural lecture, we also get to share his birthday with him. And congratulations, Prof, and may you have many more such blessings. Prof Musee was born in Kenya, where he completed his bachelor's in physics and math education, and then started a 4-year stint working as a graduate teacher in 1994. He moved to Botswana in 1998, and he obtained his master's degree in physics at the University of Botswana. He was also a tutor, moved to the University of Stellenbosch as a research assistant, obtained his PhD in chemical engineering, and was there for 7.5 years as a scientist and researcher for the CSIR. And at the CSIR, he was a co-founder of the first research group in South Africa on nanosafety research in the environment. He joined the University of Pretoria as associate professor in the Department of Chemical Engineering in 2015 and was promoted to full professor in January of this year. And at UP, he led the Emerging Contaminants Ecological Risk Assessment research group to study variant. I get very scared when I hear the word variant lately, but to study the variant environmental contaminants using integrated experimental modeling techniques. And to date, he has supervised 7 PhDs and 2 masters to completion. And he has endeavored to address the chemical pollutants in aquatic environments and has served in many steering committees, working groups, and task teams. That would be for the European Union, for the DST, Water Research Council, as an expert on nanosafety research. And in addition, as one of the leading global experts on nano wastes management, he has been consulted by Basel, Rotterdam, and Stockholm Conventions Secretariat, the United Nations Environmental Program, Switzerland, concerning research and questions requiring redress within the Basel Convention framework in 2015. He has also served as an external reviewer for many technical documents for the WHO, the OECD, and the Department of Environment of Canada. And all of us really know how big Canada is about the environment and issues related to it. And all of these aspects are related to nanosafety and antibacterial agents to humans and the environment. In 2009 and 2013, respectively, he was the chair and convener for the first and second National Conference on Nanosafety in South Africa. He has a very impressive publication record, 34 articles in ISI journals, 83 conference presentations, including plenaries, keynotes, and so on and so forth, 5 book chapters, 18 technical reports, and of course, 8 popular articles. All these work embody an interdisciplinary approach with collaborators from biological, engineering, and physical sciences domains for specialization. It is through this interdisciplinarity that Prof. Musee makes a valid contribution to deepen scholarly inquiry and enrich academic debate at our university and beyond. And in recognition of his contribution to the water sector in South Africa, he was awarded the Water Research Commission Legends Award in 2021 for being a researcher and a leader that brought national and global recognition to the South African water sector over the years. The title of his inaugural address, as the acting dean has said, is anthropogenic activities implications to aquatic ecosystems and integrated responses. Anthropogenic activities are by nature janus-faced. The societal benefits of such activities include providing water, food, health care, ease, and easing the communication. On the other hand, these activities have for decades been recognized as impacting negatively on aquatic systems. This is as a result of the sharp increase in pollution related to industrial activities and domestic toxic chemicals over recent years. And in his lecture, he will detail the implications of selected pollutants to the aquatic systems, their occurrence on local and global scales, and a risk assessment approach based on experimental and modeling techniques. I think one of the things that is quite outstanding, ladies and gentlemen, is the work that is addressing some of the sustainable development goals. And the lecture will dwell on that and what the consequences are. And the emphasis will be on 3 of these SDGs. SDG 3 on good health and well-being, SDG 6 on clean water and sanitation, and 12, responsible consumption and production. I'd like to take this opportunity to give our esteemed colleague an opportunity to address us. Prof. Ndeke Musee. Thank you very much, ladies and gentlemen.
Thank you for the opportunity for this evening to present an inaugural lecture at the University of Pretoria. I would like to thank the rectorate presented by Professor Themba Musee, Vice Principal Student Life. I also want to thank the acting dean, Professor Jan Elof. I also want to extend my thanks to the deans and the deputy deans of the University of Pretoria, heads of departments, and particularly the head of department in the Department of Chemical Engineering and colleagues, the academic and research colleagues, both in South Africa and globally, that we work collaboratively. I also want to thank the alumni of the university that are also listening for tonight's lecture, colleagues from the water boards that I work with, the science councils, and other bodies in South Africa. I also want to thank the students that I've had an opportunity to work with, both undergraduates as well as postgraduates and interns. We'll also want to thank the organizing committee of this inaugural lecture, our colleagues in the Faculty of Engineering. We have Managa, we have Suzanne and Emily and others, including the team that is really providing the streaming of this particular inaugural. And also, not least, I would like to thank my family for the support and for the love and the care that they've been able to provide me for many years as part of an academic journey that has brought us where we are tonight. Tonight, I will address an interesting issue which regards the human activities. What that means to the aquatic system is actually which provides us with a number of benefits, but also look at some of the challenges the chemicals poses to these particular systems, and then we'll be able to end up providing an integrated response to that. But first, let me extend my dedication for this because it's a birthday to my parents, Alice and David, and to many medical professions. As we present this work, we are already under pandemic, and particularly Dad was very fond of medical doctors, and to all medical doctors and those friends who have also invited as medical doctors to be part of these presentations, I'm sure you'll be able to present the aspirations of what he was aspiring. Next, let me give the outline of the presentations. For the first part, I'll be able to provide the global picture, and then in the second part, I'll be able to give a few examples of what we have done as academic, part of the academic journey, and then the last one, we'll be able to look at some of the sustainable goals, and we'll be able to look at what could be some of the issues where we can have integrated sound chemical management achieved. And then we'll look at some of the lessons we have learned across over time, and what are some of the future research directions that needs to be considered. If you look at what we have there, we have so many activities that we do have today as a part of the life supporting system. We could be able to have our industries, we'll be able to have our farms, we'll be able to have our wastewater treatment plants. We have got our houses where we live today. With all those, including the shipping, the maritime, the transportation, we use chemicals. What happens with the chemicals from the time you synthesize a molecule from the lab to the time when the lifespan of that particular product comes to an end, and then you have the materials being released into the environment? That is what we are going to be able to discuss today. But with the houses where we are, you'll find that on the left-hand side, on the right-hand side, we have looked at some of the products, and you'll find they have got hundreds of chemicals that are incorporated there. What happens with those chemicals when they are released into the environment? I'm just giving an example. On the lower right-hand side, we have a world whereby we are really singing on plastics, we are singing on chemicals. What do those really do? And those are some of the things I want to discuss tonight. What do they do to the aquatic life? We need the aquatic life to support our life as humans. We need the wildlife. We need, for example, water. We need source of our pharmaceutical drugs that we use as humans. And also we need where we can be able to get the drugs to treat our livestock. So we will be able to look at that and see what exactly happens. But these are some of the benefits that we get from the environment, which we are generically regarded as ecosystems services. And you find that they start from the provisioning. In other words, they can be able to provide us with the food, they can provide us with the water. They can also be able to, enhance the sustainability of even having cool temperatures because of the trees. On the other hand, we can also be able to have regulating in terms of the purifying water, in terms of the storing the carbons. And on the opposite side, they can be able to support things like soil formation, photosynthesis, which is good for food production as well as for biodiversity. All these ecosystem services are critical if the integrity or the health of that ecosystem is there. But what happens when the chemicals come in? Now, according to Millennium Ecosystem Assessment Report of 2005, there are a number of features that really defines chemicals. And one of them is that they have got global distribution. We will show a few examples of particular chemicals where they are all found across the globe. The second issue is that the rapid growth. We will be able to show that from the 1970s to now, there have been a rapid growth in terms of the number of chemicals in our circulation. Next, we'll be able to discuss some of the negative effects or impacts of chemicals, both known and unknown to biological lives. Biological lives here, I mean wildlife, I mean humans, as well as the aquatic life, for example, that is underwater and in the soils. But to contextualize that aspect, it is important to look at what are the current global challenges that we have today in the world. A number of scientists have already been able to categorize them to be 9, and they call them the 9 planetary boundary challenges, including climate change. They also include ocean acidification. They also include, decreasing quantities of fresh water. But one of them, which is critical, is that you will find that chemical pollution has been identified as one of the global challenges. Interestingly, it is among the challenge that is not yet quantified. And that was back in 2009, the first paper which was published in Nature. In 2015, Stefan and his colleagues, you will find that they also look at those challenges again, and they were trying to establish what are the boundaries. And you will find that what they are calling the novel entities on the right-hand side is where you have the cursor. They are yet not been able to be quantified. Why? We will discuss that this evening. One of the remarkable things that really happened is that the boundaries that were really identified in 2009, they were 3. By the time it's 2015, 6 years down the line, an extra one, especially land system change, and that is because of agriculture. And so we need to be able to find solutions on how to address these global problems, including our pollution, and we'll be able to discuss some of those aspects in this particular lecture. Let's look at some of the statistics to give context. One of the issues that you will find, and that has already been able to be a great challenge when it comes to the managing of the chemicals, is that the numbers are really changing. One of them is that UNEP will be able to tell us that there's about 150,000 chemicals. 2020, Wang writes a paper and he says it's about 350. When you look at in 2018, you are told that the numbers in European market is about 100,000. That means the rest of the world only can account for 50,000. These numbers that are really there, they also make it very difficult to be able to manage the chemicals. But there's a point that I want to be able to raise. Up to date, we have got only about 1,000 chemicals whose risks to the humans are well known and categorized. That leaves us with a big challenge because at present, or by 2009, 3 billion registered chemicals were already established globally. Next, if you look at the rate at which we work in the lab, if we were to assess all the chemicals and check what the risks are, it will take us 100,000 years. And by the way, every year that we bring in 1,500 chemicals, that will be taking us 2,000 years. So what does that really mean for us to be able to address the issue of the chemical? We need to be able to have smart testing. We need to be able to have proper prioritization processes of doing that particular work. And also we need to be able to have highly collaborative approach given the size of the problem. And those are some of the issues we'll be able to raise over there. Let's give some other context. Every year, We produce around 250 billion tons of chemicals. Secondly, when we release those chemicals or we use them as humans, about 8% of the men are infertile, linked to chemical infertility. Thirdly, in our own bodies, studies have shown that we have got about 700 chemicals in our bodies. Not only that, around every year, we have got about over 150,000 chemicals in the global market, in circulation. The market value is close to $7 trillion by November 2021. And actually, in dealing with the issue of risk, whether to the humans or whether to the wildlife or to the aquatic system, there is no law of dealing with the cocktail effects in terms of what are the mixture regulations to regulate the chemicals, whether to the humans, to the wildlife, or to the aquatic system. So that gives us a context of why the anthropogenic activities and the way we use chemicals is very critical if we will be able to attain a sustainable development. If you look at in terms of the economics, you are dealing with, in 1970, we had about $171 billion of the worth of chemicals in circulation. Today, we are dealing with around 7 trillion by 2020, by 2030 in terms of euros. So that is almost 9 trillion. That kind of volume of sales is bigger than the economy in most of the economy, all combined economies in Africa and parts of Asia. And that means the chemicals industry is very large, and we need to be able to deal with it, and that's why it has been, chemical pollution has also been flagged as a global challenge. Over the years, from 1970, most of the production for the chemicals was actually in the first world. But what has happened over the years is that that production has now moved, has shifted from the developed countries to developing countries. And why has that been the case? One is because of the cost of the disposal. Number two, there have been a strong movement whereby not in my neighborhood has made it very difficult to have access to landfills or any other waste management, or particularly dealing with hazardous materials. And thirdly, the shipping line has become so cheap such that it is easy to export the chemicals rather than to be able to manage them within the country of origin. So those are, in the combination of that cocktail of factors, among others, has made it to be able to have the shift. But what is the critical point I want to raise here is that although most of the patents for chemicals, if you look at the United States Patent Trade Office, Japan Patents Trade Office, and European Union patent offices, most of those chemicals are there, and they are, in terms of the income, they go to those countries. But when they shift them to the developing countries, most of them are lacking skills to manage those particular chemicals or waste streams which are really hazardous. And we will show the results here that when you look at the adverse effects to the human health, you'll find it is mostly in the developing countries, either in Southern America or in Africa. And so that is very critical when we're looking at the future of how we are going to manage chemicals. The developing countries also need to be able to up the game. Some of the issues, as I just said in the last slide, you'll find that now is about 63% of the production is already in the developing countries. The BRICS has also been able to increase the production from 13 to 28% from 1970s to 2020s. But what I want to point out as key here is that the global production is about 31% in the developing countries, and actually they consume 33%. So they consume more than what they really produce. And that means there are more chemicals in the developing countries than what they really produce. Just to give an example, from 2003 to 2013, 10 years, in China alone, increase in chemicals production increased by 280%. So clearly there is a need to be able to manage I'm trying to make a case here just to give a global picture of what is happening here. But what are the social and the economic impacts of chemicals in our society? Well, when you look at the climate-related natural disaster, because most of the time we talk about the climate change, so I wanted to use a relative term that is really being understood. For 2018, we had a loss of about $155 billion. In 2018, on the same year, because of the chemical pollution, we lost pollinators and a threat to the global crop output That was between 230 to almost $600 billion. So chemical imprints in the society is quite really large, even when you compare it with the well-known challenges like climate change. But at the same time, when you look at the Lancet report of 2018, you realize that, and also other studies like from Blacksmills Institute, we have been given estimates of between 8.4 to 13 billion mortalities, which are really chemical related in pollution, whether in water, in air, or in soil, or in the oceans. But of those specifically, about 1.6 million are really from the chemicals by the year 2016. Again, this shows us that the chemicals have got imprint in terms of both human life as well as economic when it comes to what they do to our society. But I want to look at the last indicator of the impacts of chemicals in the society, and that is the disability adjusted life years. What does that really talk about? If your lifespan was to be 65, but you find that you only live 35 years which are healthy, and in between there you are living with the disabilities related to chemicals, and then before even you are 65, you die about 55 years, that difference is what is going to be able to give us disability adjusted life years. And that has got a lot of implications, and particularly in the developing countries, because those numbers, when you look at them statistically, they have increased dramatically as the number of chemicals have increased in the society. Let me just give a context in terms of what the chemicals have done, just to give examples of the health effect. If you look at what has happened is about AD, they say at around the time of the AD to around 1650. That's about 1,650 years. You will find that the population doubled after 1,650 years. Around that time, when you look at the history of the chemicals in the society, you'll find they start increasing. And from there, the numbers have reduced to 200 years. You double the population. After that, it only required 80 years. From there, 45 years, now 55 years, and we expect to be hitting 10 billion in shorter while from here. What does that, why has that really happened? Two major classes of chemicals are responsible for that. One is pharmaceuticals, for us to be able to treat us. And the second one is actually pesticides for agriculture to feed that particular population. And what do we get now? According to the World Health Organization, in 2018 report, it tells us that the chronic diseases related to chemicals were about 27%, and cardiovascular was about 33%. And those are some of the effects, as I've already given examples in the previous slide. And therefore, these are having real impact into our society, including having effect on the IQ. Some of the studies are saying that we lose about 60,000 IQ points a year because of the chemicals. So we really need to be able to deal with the chemicals. Now, let me give the issues of the distribution of the impacts globally. You will find that in Africa, you will find that most of the impacts are really recorded in that particular. And the reason is because we have been having the disposal of chemicals and hazardous waste in the African countries, as well as having, skills or no skills to manage those kind of particular waste streams. You can see that in the developing countries, that has not been reported for a while, but at the moment, that's what we have in the developing countries. If you compare the impacts of the chemicals, looking at the data in a different way, you'll find that although today we talk about AIDS, malaria, and tuberculosis as some of the global, risky factors, if you compare that with the chemical pollution, you'll find that AIDS, malaria, and tuberculosis only accounts a third. Number two, the low-income countries and lower middle income, they almost constitute about 92% of the total impacts of chemicals to the human health. Those are staggering numbers, and we need to be able to do something about that, and I'll discuss that shortly. Let's look at some of the distribution of the chemicals in the environment. You'll find that based on the studies that have been done, most of the detecting the chemicals in the environment has been done in the first world. And that's why you find that although the mortality was higher in the developing countries, the detection has been done in the first world, and they have also been able to have legislation. For example, when you deal with the clean the Clean Air Act back in 1970s in America and others, when those kind of laws came into effect, you will find that they started detecting the pollutants in the environment, and that's where you'll find the red marks of where they are detected. Actually not in, mostly in Africa, we don't have that. And that is a concern because when we look at where the mortalities is, that's where the mortality is actually on the higher numbers when it comes to African continent because of the reason I've already given. Another example, ARVs. We do some work in ARVs. 1987, we had the first ARV drug, or in terms of a treatment for the ARV, as an antiretroviral drug. Around that time, nevirapine was introduced, but it's only after 2018 when the risk assessment of the ARVs was done. Studies have been done from then, and one of the key aspects is, if you look at on the right-hand side to see where the distribution is actually happening, most of those drugs are found in the environment in South Africa, and the reason is because South Africa has about 7.7 million cases of HIV, and above that is the country which has used the highest number of different ARVs. If you look at the number where the cursor is, South Africa has used 14 different ARVs to treat the AIDS in this country. And that's why you find most of them are detected in this particular country, followed in Kenya and other few countries in the European countries like Finland and others, including Germany. But what does that really tell us? If you look at the statistics on the left-hand side where the cursor is, most of the HIV issues are around Africa. And yet, we do not have a program that is really looking at what is going to be the long-term effect. Remember, when you begin or initiate the HIV drugs, the ART runs for a lifetime of that particular person, and their concentrations have been increasing rapidly over the last few years, especially post-2017, when the World Health Organization, as well as the UN, actually declared that the CD4 count will no longer be used for you to start the ART program, and that means as long as you are been found to be able to having the ARV, you'll be able to get your ARVs. That really is a key concern and is a big issue. Let me give an example of the work that we have done there. One of the issues is that in most of the ecotoxicity work, we normally look at the mortality, but we could not see the mortality for the ARVs that we are looking at. What happened is this: when we used sensitive techniques, the concentrations that we could see causing oxidative stress in Daphnia magna, for example, were much lower than the ones that were really found in the environment. And therefore, that is a concern to us. The work is continuing, but we need to be able to generate data that can be able to inform the policy makers and decision makers in this country and the rest of Africa, where HIV is really a key issue as part of, as what we have shown to be contributing to mortalities across the globe, particularly in Africa, or in the sub-Saharan Africa. Now, let me come to the science, some of the work that we do. How do we do risk assessment of chemicals? We look for two concepts: hazard, which is actually the toxicity, and to what extent do we have the exposure really happening. And so if there is no exposure and there is no hazard, there is no risk. You can have very high toxic chemical, but if it is used in a way that it is not exposed to humans or to aquatic life, there will be no risk. Thirdly, you can have a case whereby there is the risk, the hazard is above zero, the exposure is above zero, you get a risk. But the risk of different chemicals are different, and the way they are managed is different. And that's why the areas under A, B, and C, just simple mathematics, will be very different to be able to reflect that. So let me apply that concept. How do we do about toxicity work? Well, to do toxicity work, there are so many endpoints you need to be able to look at, and you need to be able to select how you do your work. What is the goal? What is the long-term goal? The long-term goal is to see how does the chemicals affect the ecosystem. For example, in terms of the productivity, to renew that ecosystem itself, how it affects the food webs, and the functioning of the entire ecosystems. But you realize that at that particular point, when you want to do studies which are, they have got ecological relevance, the time that you need to do that work is very long. and you'll find that it is very costly, and the leakages from one level to another become very low. However, when you want to work with at the molecular level, working with the bacteria, or to look at the responses at the molecular level, you can use biomarkers which are very specific, and we will give example in this lecture tonight how that has been done. And you'll also find that you can be able to say, well, with this particular chemical, these are the effects. But to be able to show the effect of a particular chemical in the environment, within the cocktail with others, is quite challenging. And that is one of the issues that we need to be able to think. So how do we propose to go that? One of the propositions we have is to be able to have ecologists and ecotoxicologists to work together. Why? Ecotoxicologists mostly work on the lower part, whereby they will look at the molecular sublethal and maybe individuals, and very rarely to work with the population. The ecology folks, they work with the population, community, and ecosystem to observe what the effects are, for example, pollution. And if you combine those two skills, among others, you'll be able to improve the way we manage our chemicals in the environment. So I'll give an example of work we have done. But before we do that, we want to give an example how chemicals and climate change, they actually have an intersection. How does that really happen? We know that climate change has been shown to be able to have a direct impact on the aquatic life, for example, by increasing the salinity because of high evaporation, the turbidity because of high floods that are happening, and even the habitat, the habitat loss, including the coral reefs. At the same time, we have the effects that are caused by the chemicals. But how does that really happen? Well, because of the flooding, we will find that some chemicals are found in places where you don't expect them. I'll give two examples as we proceed. You can be able to have the increased UV light or ultraviolet. That will increase photodegradation of the chemicals, and when that happens, they'll make it more bioavailable to organisms, and in the process, you might see elevated impacts. And if that really happens, then chances are that you're going to see alterations in terms of food web structure in the ecosystem. At the same time, you can also be able to find that when there is change in freshwater runoffs, you're going to be able to see the effects, and we'll give an example that we have done for some work here in Gauteng province. So there is a clear synergies that are between chemical pollution as well as the climate change. For example, one of the effects that you see is dilution factor. Sometimes we use the rivers to dilute our pollution. And when there's droughts, when there's a change of precipitation, you expect the concentrations to be higher, and they're likely to have impacts into the ecosystem. So that synergies need to be taken into account, and it is important that we start having work between the folks who are working in the climate change, also working with those who are working or who are dealing with the ecology of the chemicals in the environment. In our group, what we do is we have done work for personal care products, for example, for triclosan and trichlorocarbon. We have also worked with different engineered nanomaterials in terms of nano products and nano waste streams, where we have all sorts of, oxide nanoparticles, metal nanoparticles, and even carbon-based nanoparticles. And at the moment, we have started working with the pharmaceuticals, particularly with the ARVs, because we know they are among the increasing pollutants in the developing countries, particularly in sub-Saharan Africa, as studies have shown. And so let me give you an example here. We add alumina and titanium dioxide. What we did is to be able to go out there and say, okay, let's use one of the organisms. One of them is the fresh snails, the Pfizer acuta. Why did we choose it? It is widely available across the globe. It is sensitive to the chemicals. It can be able to grow very fast. And we looked at a number of aspects. First, what we did is to be able to characterize the nanoparticles, and the table there shows the different characterization that we have. But the key point that I want to show is the properties that were exhibited by aluminum oxide nanoparticles, which is the alumina alpha and gamma. And you'll find that one was positive and the other one was negative. That has got a lot of effect, because when they get into the body of an organism, one dwells longer and it will cause an effect higher than the other, and we'll show that with our results. The second one is that the size of the nanoparticles will be able to cause an effect. Thirdly, the shape of the nanoparticles, whether it is amorphous or it is crystalline, affects how they are going to be able to induce the observed effects. And the solubility, do we have ions or are they the particles that are there? When we look at the epic endpoints, which are the body-based, as well as the biological responses, these are the results that we got. First, we look at how the laying of the eggs. The modified titanium dioxide as well as commercial titanium dioxide, they had no effect in terms of the laying of eggs, whether it's after 1 week, whether it is after 4 weeks, whether it is the mass, it is egg mass. We did not see much difference with the control. However, when we look at the results for the alpha alumina as well as gamma alumina, the effects were significantly, particularly when it came to higher concentrations, and the results are very clear. Where there is a star, it shows that significant differences of the results were observed between the control and the test organism that we are really looking at. On the left-hand side, we are looking at the eggs. What you'll find there is that for these two at the top there are no effects when you put them or you observe them through the microscope when you are dealing with the titanium dioxide, whether it is commercial or modified. But if you look at the ones, we look at the results that were really presented or obtained when you are having alumina, you'll find that the eggs were smaller, they were having deformations, and in that case could account for the lower number of eggs over the weeks. When you look at the results for the titanium dioxide, there are no effects again compared with the control. So the type of the nanomaterials, the physical-chemical properties will be able to have the kind of response that you get when you have the chemicals in the environment. We are just summarizing the results here. No effects were found with the titanium dioxide and alumina. Both of them, they reduced the growth of the snails. The rate at which they were hatching were reduced. The deformations that we observed increased. The oxidative stress really increased, and actually their behaviors were observed. What behavior did we see? When you introduced the snails in a solution or in exposure media with alumina, you see them moving away. And that is to show that they are really sensitive to those particular contaminants. And that has also been observed here for fish and other types of snails to show that when there are chemicals in the environment, there is a behavioral change whereby the organism will be moving away. And those can be used as indicators of the ecological health. That is the first study that was done with the snails with the nanomaterials. We published that work in 2020. And the implications are as follows. We saw fewer offsprings per time. There was a reduction in the snails population when you expose them to the alumina engineered nanoparticles. That has got likelihood of reducing the ecosystem functioning. And of course, remember, the snails are actually predators for the algae. So chances are that the algae will be able to become higher, and in that particular case, you'll be able to find that it will be able to change the ecosystem functioning. At the same time, snails are food for higher level organisms. That means when they're going to be able to be reduced, the predators are going to go hungry, so there will be food scarcity, and that will be able to destabilize the entire ecosystem. So with those studies and others that have been conducted from 2020 to 2019, we can state clearly that engineered nanoparticles are likely emerging molluscides, or they can be used as mollucidal agents. And that is quite critical, because where they accidentally will be released into the environment, they can be able to remove the snails or other molluscides that are in the environment, or they can be used, they can be applied for that. Overall, the reduction in mental development, inability to detect predators, could be able to affect the survival strategies of the snails. They can be able to change their feeding rate. They can be able to change their energy balance, and that has got implication in terms of growth and production, and that has got critical implications. The second study that we did with one of my PhD students and now a principal researcher at the CSIR, we looked at higher aquatic plants. We exposed them to two types of nanoparticles, zinc oxide and silver nanoparticles. We took these plants, we measured them, we looked at their length, and we did some work to look at the free radical activity and also enzymatic scavengers. Just to explain a bit, when you expose an organism to a pollutant, you expect it to be able to have oxidative stress, and that's why you are measuring your reactive oxygen species and reactive nitrogen species, and also your hydrogen peroxide. There is enzymatic scavengers, in that particular case, catalase or superoxide dismutase. Those are some of the effects that really happen to be able to counteract the oxidative stress. So we will give a bit of some results to show what exactly we have done for silver nanoparticles and for zinc nanoparticles. What did we find? When we did the reactive oxygen species together with the reactive nitrogen species, this is what we found. We found that when it was at 0.01 concentration of the zinc oxide nanoparticles, what happened is that you'll find the oxidative stress increased dramatically. Why? We were suspecting that it is the particulate effect because there was not much solution at that particular case, especially at after 4 days, that is 96 hours. However, when we look at the zinc oxide again after 14 days, the dissolution of that zinc oxide nanoparticles increased, and that could be able to explain the increasing effects as over time, which is dependent on the concentration of exposure. Let's look at the case of the silver nanoparticles. That was another interesting case because silver nanoparticles had very low dissolution, and therefore they gave us inverted bell-shaped effect. In other words, you observe higher, rose on the lower concentrations, but actually on the highest concentration of over 1,000 milligrams per liter, nothing we could be able to observe, and at that particular case, no single plant survived, so we could not be able to expect any effect. So overall, these results show that the effect or how the nanoparticles attack the organisms is dependent on the type of the nanoparticles as well as the time factor. And of course, on the right-hand side, we saw the effect was higher for the zinc oxide because of the dissolution, because in that particular case, the particulates as well as the ionic species were together, and those synergistic effects could account for the observed increased effects. Hydrogen peroxide also gave the same kind of curve, but you'll find that the effects were more pronounced when it came for 14 days. The effects were higher, and some of these results are showing that when we do very short studies, for example, 72 hours, 48 hours, or 96 hours, we may miss certain aspects. So it is important to have clonic studies to be done for the exposures to be able to get a full picture of what those particular pollutants can do in the environment. These results are showing that. This is now the production of the oxidative stress. What exactly happened in terms of counteracting that? Well, we have the total, the TAC results. The TAC results are also showing that there is a relationship between the TAC and the ROS, the one that you will be able to see. And one of the things is that, again, the particulate effect was observed for the zinc oxide, and you'll find that the combined effects could have already been able to have that for the silver nanoparticles, especially at the highest concentration, because there we got about 1.2% dissolution. On the other hand, the results for the TAC after 14 days for the silver nanoparticles could not be determined. There was no particular trend, and that is something that we need to be able to investigate why that has really happened. We've not been able to explain those particular results, and it remains to be an open research question. However, when you look at 4 days, you will find that the effects for the zinc oxide are normally not very different from the control, except for 0.01 milligram per liter. After 14 days, you will find that the effects are decreasing, and that means when you have the, the oxidative stress, it is diminishing the capability for that particular organism to respond to the pollutants. Why is that possible? One of them could be due to the protein degradation, and or it could also be due to the fact that the subcellular mechanism of the organism has always been diminished through the exposure to the engineered nanoparticles. When we look at the SOD, superoxide dismutase, that was an interesting case because at one point you'll find that the effects are activated with the silver nanoparticles, especially on the lower concentrations, but at the same time, in the middle, for the middle concentrations of 0.1 and 1 milligram per liter, you'll find an inhibition. A similar case was also observed for the zinc oxide after 14 days. How do we explain this particular case for the SOD, whereby you have an inhibition effect as well as activation effect? This is the reason why you're observing that. One is that when you have the SOD as an oxidant activity being activated for an organism, it can be activated or inhibited. Once the oxidative stress really occurs, you will find that you expect to be able to have the effect being activated. However, once it is at a particular level, the process happens in such a way that a reverse really happens, and that is particular case that we observed for this particular case, and that is quite an interesting one. But for the 4 days, we observed a very high effect for the zinc oxide. We could not really understand why that really happened. We look at the agglomeration results, we could not be able to explain with that. We look at the dissolution results, we could not be able to explain with that. We look at the media characteristics, we could not be able to explain. So that remains a mystery in that particular case. But the others, we know that SOD can be activated or inactivated, and those results have also been observed in other studies across the world. So what are they concluding? There is evidence of free radical generation that can be able to increase and influence antioxidative defense mechanism for both nanoparticles that we had, okay? And that could be able to give us a possible toxicity route that could be able to explain the effects that we observe for these particular organisms. One of the things that we observed in this particular study is that we found that the concentrations that we could observe effects was about 10 micrograms per liter. In other previous studies by that time was only be able to be seen in 1,000 milligrams per liter or 5,000 micrograms per liter. And therefore, we could show that at very low concentrations of the nanoparticles in the environment may have an adverse effect at detectable concentrations to aquatic higher plants. Next, we also found that the effects were ENP or engineered nanoparticles type, the endpoint that you are looking at, and they were time dependent. We could not be able to establish the direct link of SOD and ROS, but we have already said that those things, they can be able to happen simultaneously for the SOD, and therefore we were not worried about that because that is observed elsewhere and it normally happens in plants. One thing you'll find is that the SOD was related to the hydrogen peroxide effects, and ROS was related to the TAC. So we can actually be able to say the results that we are having, we could be able to have attack and a response. In other words, the oxidative stress that you are really having and the attack that is going to be able to be generated could be linked when you are using multiple lines of evidence. What did we learn out of this particular study? One, both of these nanoparticles, whether they are metals or whether they are metal oxide based, they can be able to have particulates as well as ionic species causing the effects observed. Two, they can be able to pose risks to the aquatic plants, and therefore that can affect the health status of that particular aquatic system. Thirdly, when you look at multiple endpoints, you'll be able to get a better outcome. You can see that the TAC is related to the ROS and RNS, as well as the SOD was having results which are related to hydrogen peroxide. So if we had a fewer endpoints, we could not be able to see that kind of effects and also explain what exactly is happening in those particular case. Let's go back now. We have done the toxicity work that we do in the lab. Now, I want to look at the case of modeling, and that one I'll be able to show. We have done that for the antibacterial products in our houses. We've discussed that case. We have also done that for the nano products for the city of Johannesburg. But let's look at the case of the antibacterials, triclosan and trichlorocarbon. In 2015, I read an article whereby issues were being raised about triclosan and trichlorocarbon. Bans were being proposed across the globe. It was a Sunday Times paper, and we look at it, and then we went with the 4 years to the market, look at the products that are there in South Africa, which are containing triclosan and trichlorocarbon. We got 128 products containing triclosan in South Africa. We got about 52 for trichlorocarbon. And then we did the modeling. We said, what is actually the risk here for any of these particular specific chemicals in the aquatic system? And we used Gauteng province as the case study. When we look at those results, we could be able to calculate the predicted environmental concentrations and also look at what has been reported from a number of studies that have been done in South Africa. One of the key findings we found is that the predicted environmental concentrations, the PEC, were actually on the lower side of the measured environmental concentrations. And the reason is because when we are collecting our data for the products, we may have not collected all the products in the South African market. The second reason is that measured environmental concentrations are what we call grab studies, where you grab it in a particular specific point, either in a river or in a wastewater treatment plant. When you are doing predicted environmental concentrations, you distribute the concentration across the whole region, and therefore that could be able to explain the differences. But nonetheless, the studies are good enough to be able to show that triclosan will be able to have risks based on our predictions into the aquatic system. And the numbers that we are having, and this is something that I want to point out here, when we compared the measured environmental concentration that we found in South Africa, they were almost 100-fold higher than elsewhere in the world. Those concentrations are really, really high, and we need to be able to look at that because they can affect our wastewater treatment plants, especially if you look at the influent and the effluent, which is actually representing the incoming wastewater in a treatment plant and outgoing wastewater treatment plant. That needs to be looked at into. For the trichlorocarbon, the TTC, in many of the cases, the risks were not really there because the RQ value must be less than 1. When you're going to be observed no risks, and it should be above 1, then there will be risks. So in the fresh water is only where we could be able to see some effects for the TTC. This is what the first study that was done in that kind of a work, and we'll be able to explain the results. So graphically, those are the results. When you look at the algae, most of the algae, you'll find that on the A on the left-hand side, top left, you'll find that most of the algae are negatively affected by the triclosan because most of the values are above 1. However, in the soils, which is the terrestrial, there is no risk when you apply our solids or biosolids in terms of treating improving the agricultural output using the sludge that we get from our wastewater treatment plant as the practice in South Africa. Again, Taffinia magna and the fish were not affected by triclosan. However, when it came to the clonic studies, you'll find that some fish were being affected on the left-hand side where the cursor is. You'll find some fish were now being affected, and even some bacteria were being affected in the environment. So that is very critical to be able to notice that for the shorter studies, you may not be able to pick the effects. But when you do the studies over a longer period of time, that is very critical. Let me make a point here. Many of the chemicals, thousands of them, acute toxicity, short studies, less than 96 hours have been done. But in many of them, above 96 have not been done. Therefore, most of their risks in the environment, as these results are showing, are unknown. When it comes to the triclosan, you'll find that there are few cases where the data actually for toxicity was very few. Let me point out that. And in many cases, you'll find that for the acute, most of them are above 1. We have already shown that in the previous table. But you also realize that for the clonic studies, especially in the terrestrial, you find that that effect is not really there. So although they come from the same family, the way the chemicals in the environment causes, the effects are very different, and it is dependent on their molecular structure. So what are the key findings here in this particular case? One is that in fresh water, you find high variability of risks which are posted by the triclosan, which was about 2 to 232 values above 1. In the wastewater, whether treated or untreated, you find that for the bacteria, some of the cases were observed to be having RQ values above 1, and therefore triclosan could be able to pose risks, but that was not observed for the triclosan. And I'll tell you what the implications are just shortly. There were no risks that were observed in the terrestrial or in the soil systems. This is the first study that we try to quantify the TTC, triclosan in the environmental matrices, using the actual products in the market in a specific area. And the values that we were getting were dependent on the product category, and that influenced the levels of risk that we could be able to observe. Now, what is the significance of this study? After we produced these results, we were conducted by Canada Health and Environment Department, and we could be able to look at their document whereby they burnt the triclosan and they approved the replacement will be trichlorocarbon. So models can also be able to help us to understand what the risks are, to be able to get the value of the ecotoxicity studies that are done in the lab. You combine that with the exposures that are done, that are really be able to be done in the environment. Let me come to the sustainable development issues. Now, with all the discussions that we had here, we were trying to show some of the results, the challenges that we have regarding the chemicals in the environment. The question that we need to be able to have is, have we achieved sustainable development goals linked to chemicals? I will only pick 3. There are many. Remember, there are 17 of them. I'll pick 3 of them. I'll take 3.9. We said, well, by 2030, substantially reduce the number of deaths that illnesses from hazardous chemicals. What does this discussion that we have here? We said we will need 100,000 years for the chemicals that are there. So is that going to be doable? Perhaps there will be rapid testing and rapid techniques that are going to be developed in the next 9 years. That remains an open scientific question. Let's look at target 6.3. Improve water quality, wastewater, and safe reuse in relation to the chemicals. If you look at the chemicals today and you detect them, you find some are detected in our tap water. A lot of them are really detected in very high quantities in the wastewater, as I've shown for the case of triclosan, and we can do that for most of the organic chemicals that we have. Our water quality issues in this country and elsewhere has been raised up. So the question is, by 2030, are we going to be able to have that? Again, unless a miracle happens in the next 9 years, because already we are in December, that is unlikely. But the target that I find quite interesting is 12.4. Achieve responsible and sound management of chemicals and waste. It raises a red flag, and the question now goes on the screen and says, have that been achieved? A discussion that happened between the UN and WHO in 2015, there were indications that has not been achieved, and I could not be able to see any defensible data to suggest that that has already been. So there's a lot to be done to be able to improve how we are going to achieve responsible and sound management of chemicals and waste. And I think that is becoming a big research issue, not only in South Africa, but globally. This is among the last slides that I want to give a few issues. Now, what happened is this: when the issues of climate change arose, Intergovernmental Panel for Climate Change was formed around 1990s to address the issue of climate change. They started producing reports, and around that time you'll find that whether it's habitat loss, rising carbon dioxide, global diversity, the issue of nitrogen or phosphorus pollution, or even synthetic chemicals that we talked about today, the papers around 1990 were almost the same. With the advent of the IPCC, the first one, you will find that the numbers for the climate change increased dramatically over the years. Secondly, there has also been IPBS, that is in the panel for biodiversity and ecosystem services, has also been formed around post-2010. And the papers have also increased in terms of understanding habitat loss. Look at the a global planetary problem or called synthetic chemicals. The papers have been very, very low. They only account a fraction of 0.02. And I think that can be able to explain why in many of the cases we will not be able to manage the chemicals. So what am I proposing? I believe we need to have in the panel for chemical risk assessment in aquatic system. There's a paper in Science that has also been able to propose that. And I believe that the developing countries and countries in economies in transition like South Africa should be able to be part of that. Why and why I suggest that is really there? Because the data regarding chemicals in products will become more readily available. That research gap will be addressed. Number two, you cannot be able to address the issue of chemicals unless you deal with their mixtures. Remember, when we are dealing with the statistics, we said we don't have such a regulation around the world. That needs to be able to be put into consideration. Number three, to do that, you also need to be able to understand the complete life cycle of particular chemicals in particular services as well as products. And therefore, that needs to be done. Again, that interpanel for chemicals risk assessment in aquatic system becomes very critical to enhance that. We don't know how much of these chemicals are released into the environment. We are talking of 350,000 chemicals. How do we be able to have a smart way of dealing with that? We need such a system whereby scientists across the globe will be able to work collaboratively and generate such data. One of the key things that has really been able to hamper the way the chemicals are managed is that the absence of cause and effect, the causality effect has been really a big issue. And therefore, that needs to be able to be done for the humans, for the wildlife, and the aquatic life. And I think with these kind of issues that we are proposing here, as well as the gaps that are there, we can be able to close up. So how do we deal with that? That is the slide I want to be able to finalize with. We want to bring everybody on board. Industry, government, regulators, scientists, consumers, and again, regulators again. Everybody has to be there because with a large number of chemicals, it cannot just be one particular, it must be the whole society. How is that going to be done? Well, there should be thorough screening of new chemicals that are going into the market. Pre-market authorization should happen only when you are going to be able to give us the data. The testing criteria should be transparent, systematic, and should be doable. That needs to be able to happen, and that should be able to happen between the government and industry to establish that. When it comes to the government and the regulators, they'll say, well, if you're going to be able to give you the pre-market authorization to take your chemical into the market, we will be able to screen it, prioritize the levels of risks. We can be able to ask you to go and change particular things, including green chemistry. The testing criteria should be transparent, should be doable, should be able to be auditable, and there should be clearly well-set standards. That is another way of trying to be able to enhance that. But we don't stop there. As a scientist, we'll be able to set up what are the environmental quality that we need to be able to see. And that will be based on robust models that are developed and scrutinizing the products carefully to understand what are the releases, how much is going to be released, because we have already indicated that that data is really lacking. We also need to look at the consumer products. Market, if I remember in 1975, the reason why lead was removed from the petrol is very simple. The industry that was beginning to make platinum catalytic for the cars was saying lead is actually making life difficult. And when they got in the boardroom, the words these are the exact words that were used. They said, lead is out. Market, the consumers of the products can be able to control what is going to go to the market. And therefore, we can be able to say which ones will be able to come in and which ones are not going to be there. And the models that are going to be developed by the scientists should be reliable and credible. They need to be able to have the credibility. And lastly, some of the chemicals, once we found that the risks are intolerable, there should be bans. Triclosan they wanted to be able to ban triclosan back in 1974. That is the first case when it was taken to the courts in the United States. It was only banned in 2017. So bans should be able to happen, and they should be able to happen in reasonable time. Number two, certain chemicals should be used under strict restrictions. And that has already been done for fragrances. International Fragrances Association, there are particular fragrances that we find in our personal care products that are only used under very tight restrictions. And that needs to be able to happen for particular classes of chemicals. I'll give an example. We are working on a COVID project. We are looking at sanitizers and disinfectants. 4 chemicals are highly restricted and or banned for fragrances, and they are widely used in 4 brands in South Africa. We need to have that restriction, and that's why regulators become very critical as we speak right now. And there should be green alternatives that are being introduced into the market to be able to achieve a better world that we need to be able to have. The work that we have been able to do, and this is a good example that we have already seen from the engineered nanoparticles, is that the risk assessment for engineered nanoparticles in the aquatic system started in 2004. The first paper was done by Eva Obadosta for fish. And by 2015, there were so many papers that have been published, but not only published the papers for the sake of publishing the papers, they were converting them into policy and research frameworks to address the potential risks of engineered nanomaterials in the aquatic system and to the human health. And so these are some of the, documents in the world that have already cited the work that we have done for the nano waste, responsible management of the waste nanomaterials. The first classification for the nano waste was done in South Africa and was very used much by the European Union. It has been used in OECD, it has been used in Finland, it has been used in France. And also we could be able to do that while I was in the CSIR. We could be able to publish a sort of a booklet for Africa on how to manage the engineered nanomaterials in the aquatic system. So that is what needs to be able to happen in the future emerging chemicals that we are going to be able to have. We not only just generate the data, but that data should go to the policy, should be able to go to legislation and to the guidelines. I would like to thank the WRC. One of the things that they normally do is what we call national surveys. Such similar data need to be done for other kind of chemicals and different kind of chemicals, different kind of industries in South Africa, because that is how you begin to translate basic science to applied science. It goes to the policy and begin to increase value to society. When it comes to the global health, colleagues, friends, and listeners, and the entire world, there is nothing like them. It is all of us. And so that needs to be very clear in all of us. We cannot be able to say it is the industry, it is the government, it is the consumer, it's the regulator, or anything in between. It must be everybody. So let me summarize what we have learned out of this particular. One, there is high growth of chemicals in the environment, which many of them have got undefined risks. Number 2, and that means we need to be able to develop robust risk assessment models and protocols if we are going to be able to keep our ecosystem healthy. Science-driven decision-making needs to be there. We cannot just do science for the sake of science, especially in the developing countries and the countries with economies in transition. We need to be able to have that properly and well managed, because we need to be able to protect the vulnerable populations, the young and the old. There are so many data gaps. We need to fill those gaps, and that can only be having more studies. And I believe in the panel, for chemical risk assessment, we'll be able to enhance that. We also need to be able to train different professionals. It is not just ecotoxicologists, it's not just ecologists, it's not just biologists, chemists. We need medical professionals, sociologists, folks from the humanities, psychologists. We need to train the guys in the bureaucratic systems, because chemicals is, for the first rule should be first do no harm, and that includes everybody. So we can be able to protect our human health or the environment by training the professionals and having highly collaborative work. It's interesting that this lecture is being given in Future Africa. I believe that will be the future of the chemicals. We need to have everybody coming in and be able to look at this problem from different perspectives. Why am I talking of sociologists? It may look very interesting, but remember, if you have got the Basel Convention, Rotterdam Convention, Those are the professionals who develop, for example, frameworks for be able to evaluate to what extent it has been implemented and how the bureaucratic system and enhanced or inhibited the process. So we need to be able to have that. It's nice as a scientist for me to produce the results, have the findings be put into those kind of protocols, but how do we test that has already been affected by the bureaucratic systems? We have shown an example where there is a link between the climate change and the chemical effects into the environment. So in the future policy and regulatory framework, we need to be able to say, when we are developing a policy, we don't just look at the chemicals, the pollution. We don't look at the climate change. It's not just a matter of the fresh water or habitat loss. We need to be able to have synergies being looked into, look at the complex interplay so that when you develop a policy and a regulatory framework, it does not negate of the other initiatives that are done in other planetary problems. And I think that will be able to enhance how we are going to be able to deal with this one. It remains today an even distribution of chemical burdens across the world, and particularly in the developing countries and the countries with economies in transition. That brings into play the geopolitics. And that is something that we cannot be able to look at the sustainability of how we are going to be able to deal with the chemicals for now and in the future. Therefore, how we are going to be able to enforce international protocols need to be able to look at that particular case. I believe we can have a livable future looking at some of the issues that we have been able to discuss tonight, and we can be able to change the scenario that we have of our current world that we are able to have. I would like to thank my wife, Eunice Gina, for the support that you'll be able to give for me over the years. Thank you so much, most appreciated. I'd like to thank our daughter, Kathini. Thank you so much for the support and for bearing with us in some of the long days that we'll be able to be away because of the work that we do. And we really appreciate for that particular support and the rest of the family. Those are the collaborators that I've been able to work with: University of Pretoria, Curtin, Australia, Stellenbosch University, Johannesburg, University of Johannesburg, Botswana International University of Science and Technology in Botswana, Clemson University in the United States of America, JW Solution in Netherlands. They were working with the cosmetics, and it was a very interesting project that we were working, and also the CSIR. Thanks to the students, undergraduate, postgraduate, and interns that I've been able to work with, and colleagues. And thank you very much for my mentors. Professor John Koma said, the word training in the postgraduate is training the mind to be able to think. I'm from a physics background. I can be able to deal with ecotoxicologists because the mind was trained. Chris Aldrich, professor, I learned from him how to be able to write a good paper, be critique, and be able to see the mistakes from what you learn. Professor Leon Lorenzen, I want to thank him. He taught me how to be a good researcher, how to write a good proposal. I think I wrote a lot of proposals when I was a postdoc, as well as after I finished being a postdoc. Pete Ashton, he taught me how to be a scientist and a professional at the CSIR, how to conduct yourself, how to write, how to think, how to carry research in the field. There are very many challenges, and I think that is very critical. We have found it very useful when we are really going out there and collecting samples under COVID. What Dr. Pete Ashton has told us has become very handy. Thank you very much. Water Research Commission, thank you for the funding. University of Pretoria, thank you very much for the funding. Department of Science and Technology, currently today, the Department of Science and Innovation, thank you for the funding. National Research Funding, thank you very much for the funding. And Umgeni Water as a water board in South Africa, thank you very much for the funding, for the projects that you are working collaboratively, including the COVID-19. And thank you so much for the listeners, for the opportunity to listen to the inaugural lecture tonight. Thank you so much. Thank you once again.
Thank you, Professor Musee, for a very informative and very interesting lecture on anthropogenic activities, implications to aquatic ecosystems, and also an integrated response. In reflection on your lecture, I have the following remarks. One of the defining features of chemicals, as you have mentioned, is its wide use across the globe, but mostly with unknown risk levels, and specifically with regard to the impact of those chemicals on human life and the environment. It is clear that there is indeed a need to balance the benefits of chemicals to society against potential negative impact on human health and the environment. Furthermore, the uncontrolled growth of chemicals, as you have clearly indicated in your presentation, may become a threat to the quality of life they seek to improve, if ineffectively managed. In today's world, chemicals are indeed key global environmental change agents, and we need sufficient and reliable data to set the boundary threshold for chemical pollution as an agent of global change. As indicated by Professor Musee, it is important to engage in systematic research and gathering reliable data to improve chemicals management. I further agree that an international panel for climate change with the focus on chemicals management should be established. This is supported by the fact that there is an urgent need to adopt approaches that strengthens the integration of basic and applied research to improve chemicals management towards achieving specifically sustainable development goals, as you've indicated, and the associated targets. As indicated, it is necessary to train professionals with respect to their social and ethical responsibility, and as you've said, first do no harm to the environment or human health. The training should extend to industry as manufacturers of chemicals. This may include setting standards geared towards the use of chemicals that promotes the attainment of these sustainable development goals. Over 90% of deaths from air and chemical pollution are in the developing and industrializing low and middle income countries. Furthermore, in the last few decades, there has been an increase in chemical production capacity from the developed to the undeveloped countries. This matter is compounded by high disposal and management costs of hazardous waste streams and onerous legislative developments in the developed countries. Finally, attention must be given to effective regulatory development, especially so in developing countries, and an enforcement of international protocols to even the implications of chemicals to society in the large. I would like to thank Professor Musee for participating in today's inaugural address, given his many commitments and obligations. Special appreciation goes to the EBIT team under the leadership of our faculty manager and our marketing colleagues. Lastly, we would like to thank Louis Klute Productions for tonight's live broadcast and also for the technical support for the evening. Please be on the lookout for other expert lecture series forthcoming by our esteemed professors and researchers at the University of Pretoria and in our Faculty of Engineering, Built Environment and Information Technology. Thank you all for attending this virtual inaugural lecture. And of course, very importantly, vaccinate, stay healthy, keep safe, and I hope you will all have a good evening. Good night.